Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon to all of you. So I think we continue our discussion on the Norton circuit for this circuit. Okay. May I ask you whether maybe you have done this? Calculate the Norton current IN and also RN. Whether you can get these values IN, okay, because by using Thevenin circuit and then transform, so you should get around maybe I don't remember the value, which is 656.5. Okay, from the source transformation is 656.5 with an angle of negative 90 degrees milliampere. Okay, this is actually after the source transformation. But yesterday I leave you with this solution with the I leave you with the methods, the steps, okay, that we have already discussed. Okay, so have maybe one of you or a group of you maybe have done this, whether you obtain the value or not. Can someone share whether cannot? Okay, so some of you said that they cannot obtain the answer, which is yes, you cannot obtain the answer because the step that I show you is actually not correct. Okay, so let me show you why it is not correct, why you cannot proceed with that kind of step. Okay, so in previous step, in previous class, what we do is actually by selecting this, right? This is the branch, okay, the first branch, and then this is the second branch, okay, and then what we do is actually to get, for example, this one is Vx and this one is Vy. So I just use the voltage division technique, okay, right? For example, this one is 13 minus J5 over 23 minus J5 multiplied with the voltage source, which is 30 degrees. Okay, and then after that you can get the current, which is IA. So IA is Vx over 13 minus J5, right? So this is actually wrong. Okay, you cannot use the voltage division technique here. Why? Because you have this link. This is actually a branch that connects the first and the second branch, meaning that this right now, these elements, negative J5 and 13 with this is actually parallel. Okay, they are parallel. Why? This is parallel. Okay. Okay. Why you cannot proceed with this with this step? Why? Okay. So let's say, for example, can you calculate for me what is the value of the Vx when using this voltage division technique? Can someone of you calculate it, or maybe you can share your answer? If not mistaken, it's around 53.25, right? And 22 degrees. if not mistaken.
Hello, Doctor.
Yes.
It is 53.26 and 21.23 degrees.
53.26.
26.
Okay. And then the degrees is
21.23.
21 point.
23.
Okay, thank you very much. Okay. Okay. So this is Vx. Can someone calculate for me what is the value of this one? The voltage across 12. This one may be Vz. Can someone calculate for me by using voltage division technique? So 12 over 8 plus J6. Oh, sorry. Not J, not 8. This is actually 8 plus 12 is 20 plus J6, right? Multiply with the voltage source, 90 30 degrees. Because why? Because this is actually same, 90 volt 30 degrees, right? So that's why I use a voltage division. So can you calculate for me what is the values for Vz? Vz, the voltage across 12 ohm. Uh, 12 over 20 plus 6. Oh, mode complex. So 12 over 20 plus 6i. And then multiply with the voltage source. So, and then convert into a polar form. So my answer is 51.7 with an angle of 13.3 degrees voltage. So can you see what's wrong here? Can someone show me what is wrong with this voltage division technique that we use?
Doctor,
Yes.
I think if we want to use the voltage division technique, we can let the 10 ohm with A plus J6 ohm to become.
Yes, correct. You are totally correct. That is what I want to lead. Yes, you are correct. I want to show you why we cannot use the voltage division technique here. Because as you can see here, thank you very much for the comment, okay? I appreciate that. So actually, as you can see here, this point and this point is connected because we short-circuited this branch. Okay, so right now, these elements is parallel with 12 ohms, right? So if parallel, meaning that the voltage across here, Vx, should equals to Vz. Is it correct? It should Vx should equals to Vz because parallel. So anything, if you look carefully, if anything that is parallel, for example, you connect with a 12 volt batteries. So this voltage should be 12. This voltage should be 12, right? So because these two elements are in parallel. So same like this. These two elements, this element and these elements are in parallel connection. Okay. So the voltage across them should be equal. So if Vx is 53.26 with an angle 21.26, the Vz also should have the same values. But if you see by using this formula, voltage division technique, the V-exact value is not the same. Okay. So meaning that what we have done yesterday is not correct. Okay. So please don't do that in your test. Okay. I hope you get what I mean. Okay. Any confusion on this one? You cannot use if you have this branch connected to the second branch here. So this is actually parallel. So you cannot use directly, for example, to get the voltage here by using voltage division technique and so on. No, cannot. What you need to do is we can use the voltage division, but you need to, by what your friend said, is actually you need to combine both. Okay, you need to combine, for example, this one. So since we know that they are already parallel, okay, so what you need to do is to get this one is Vx and this one is Vy. But right now, this element is 13 minus J5 parallel with 12. Okay. While with the Vy, what you need to do is actually you need to parallel the resistor first. So 10 parallel with 8 plus J6. Okay. So can someone or maybe using calculator here. So 13 minus J5 multiply with 12 over this one is 25 minus J5. So I use bracket here. Okay, divided by bracket 25 minus 5i. So usually I prefer to use polar form. So 6.56 negative 9.7 degrees ohm. Okay. And for this one is 10 multiply with 8 plus J6 over 18 plus J6. So this one, I think 80 bracket 80 plus 60 I over bracket 18 plus 6 I polar. So 5.27 18. Okay. So now you can obtain what is the value of the current. Should be the same, right? Because it is parallel. Okay, let me. Okay, so then we expand this circuit. We expand back. So this one element, this is 12 ohm. Okay. So this is 13 minus J5. This is 12. This is 10. This one is I think this element is actually 8 plus J6. Okay, so you need to calculate. So this one is your IN. Okay, this one is your IA and this one is your IB. Okay. So right now we can calculate your Vx and Vy right now. So your Vx is actually by using the voltage division technique right now. Okay. So this one is okay. So you need this one better pakai rectangular form lah. This one. Okay, ataupun tak apalah. 6.56 negative 9.7 over the total impedance 6.56 negative 9.7 plus 5.27 18.43 multiply with 90 30 degrees. Okay, so double check. You can do it by double check whether my answer is correct or not, because sometimes when I click this online calculator, so I maybe miss click the button. Okay, negative 7s over 6.56 angle. This one saya buat dululah yang pertama ni, bawah dulu. So negative 9.7 and then plus 5.27 with an angle of 18.43 and then bold dengan 5.6 angle negative 9.7 and then baru inverse. Okay, and then baru multiply with the voltage source. So in polar, so you should get 51.4, 17. Five degrees. Okay, and then your Vy ni is actually you just 90, 30 degrees minus 51.4, 17.5 lah. Okay. So, because it is series, 30 minus 51.4 angle 17.5. Okay, convert into polar, so 41.3, 45. Okay, so after that, so I can calculate my IA. My IA is over 13 minus J5. So 51.4, 17.5 over 13 minus 5 I. Okay, then in the polar form 3.69, 38.5. Okay, and then let's calculate the IB. So our IB is 41.3, 45 degrees over 10 ohm. So this one should be 4.13, 45 degrees. So your IN is IA minus IB. 3.69 angle 38.5 minus 4.1345. Yeah, we get 0.624 with an angle of negative 92.3 degrees. I think which is slightly different. Yeah, the answer is around 656. Okay. The answer should be 656, 0.656, but I think maybe we do some round up here. So, but it is acceptable for me. Okay. Because usually I will look at the method or the step that you take to have this answer. Okay, so we done here. We obtain the answer. Okay. Any questions? Okay, thank you very much. Okay, so let's proceed with the same circuit. Okay, but I put an extra question. Okay, for example, using this circuit, so the answer is VTH is 7.415, negative 84.68. Okay. So based on the question, so I have already obtained my, for example, my equivalent Thevenin circuit, which is the voltage value is 7.415. with an angle of negative 84.86. And my impedance Thevenin is 11.243. And J with an inductor of reactance 1.079. Okay, so this is the equivalent Thevenin circuit that we have already obtained from the circuit. Okay, so my question is, if the circuit is connected with a load, unknown load, which is impedance load, okay, unknown, what is the value of, you estimate of the Z load for the current, load current here, IL, is in phase with V Thevenin. So the answer is, the question is, what is the estimated value of the load so that the current load IL is in phase with the V-terminal. Okay, that is the question. So I give you around maybe 5 minutes to think about the answer. If you have obtained the answer, you can privately message me through the chat room, okay? Okay, 5 minutes. Get the values of the load so that the IL is in phase with the V-terminal. Okay, so anyone give it a try? So no one have chat me, message me. So what is the estimated value of the Z load for the current is in phase with the V-terminal? What should you do? What should be the load? To do calculation actually. From the circuit, you can actually calculate. Not calculate, you can just give the value. So one of your friend say that the value is 0. So okay, so Z load is 0. So if you want to check, you can check. So if Z is load is 0, so meaning that you can calculate your IL, which is your VTH over the Z total, right? So your VTH is 7.415 with an angle of negative 84.86 degrees over the 11.243 plus J 1.079. So if you calculate, I think you should get, actually the values, okay, let us calculate. So this one, if in polar form, in the thing, in a polar form is around 11.243 plus 1.079 I. So 11.29, 58, 11.29, 5.48 degrees. Okay, so 11.29, 5.48 degrees. So if I plot the phase diagram, so my VTH is here, negative 84.86 degrees. So this is my VTH, while my IL is here, 5.46 positive. So 5.46, very small, the angle. So this is my IL. So still, this is in phase. What you need, meaning that in phase, meaning that your IL should be, if this one, your VTH is this one, so your IL should be also this one, right? Meaning that your IL, the angle of the IL should be also negative 84.86 degrees. So how to make sure that your IL has the same angle with the VTH? That is the question actually. How to ensure that the angle of your current is same with the angle of the VTH. So that is what called in phase. So right now, if I put your Z load is 0, and you got the answer here, and the answer shows that your IL is not in phase. Okay. Okay, IL. So maybe there's some miscalculation. What is the answer? Yuin, the value for the IL if the Z is 0. Maybe I mistype something. So that's why maybe but doesn't matter, because meaning that one of your friend answer where it said Z is equal to 0 is incorrect. Okay, so meaning that this answer is also incorrect. Okay, so your friend answer is 0.6. Oh, this Yuyin, are you referring to the previous answer here? The previous question? Yuyin? Oh, from the answer from the IL. Okay, thank you very much. Oh, maybe. So 6.656 angle negative. So okay. But still, okay, so this one, if I plot back, okay, based on the new answer, so this is my VTH, which is negative 84, if not mistaken, 86. Okay, and from Yuyin answer, my IL should be 0.656, very small. Okay, so this is my IL, so negative. Okay, negative 90.34 degrees. Okay, thank you very much. So still, the IL and VTH is not in phase because there's a different angle. So this is negative 90 and your VTH is negative 84. Okay, so still not correct. So if you set Z load is 0, so your answer is not correct. Okay, but one of your friend just messaged me. He said that the Z load here, to make sure that the current is in phase with the VTH, you set the Z load is equal to the negative 1.079. Okay, so let's check. So when you set your Z load is equal to negative J1.9 ohm, okay, your I load is VTH over 11.243 plus J1.079 minus 1.079. Okay, so right now this one is cancel up, okay, because positive and negative, so meaning that your this one is VTH 11.243 with an angle of 0 here, okay, because only resistor are exist. So this one is 7.415 with an angle of negative 84.86 over 11.243 ohm, okay, because resistor only. So based using my calculator here, 7.415 over 11.243. Okay, so my answer is 0.659 with an angle of negative 84.86. Okay, so as you can see, the load current are right now, the angle is in phase. If you're not convinced yet, so let's plot the phase diagram. So this is your VTH with an angle of negative 84.86. And then the current value, which is a smaller, but the angle is same, negative 84.86. Okay, so negative 84.86 degrees. So as you can see, the current are in phase with the VThevenin. So for the conclusion here is that you need to know the relationship. Okay, we go back to the basic, the relationship of the voltage and current for every element. For example, when you have a resistor, okay, when you have the inductor, and when you have the capacitor, or when you have the both RL, RC, and RLC. So you go back to the basic. Okay, so here you can see that to get the current to be in phase with the voltage, the main thing, the only element that can provide this kind of in phase, okay, in phase is only resistor. Okay, only resistor. If your circuit contain resistor, your voltage and current will always be in phase. Okay, if you have another element, for example, inductor or capacitor, your voltage and current will be not in phase. Okay. Okay, the inductor and capacitor will actually affect the phase difference between the voltage and the current. The only element that can give the voltage and current are in phase is only if you have the circuit contain only resistor. So right now, from the circuit that we have simplified, okay, where we have the Thevenin voltage and the impedance Thevenin. The impedance Thevenin right now contains resistor and inductor. Okay, so in order to the current load here to be in phase with the voltage V Thevenin, which is the Thevenin is negative 84.6, the only way is actually to what is called to eliminate the inductor effect here. Okay, so the inductor is positive, so you need to put the Z load a capacitor. Okay, so XC, your load, your Z load is actually a capacitor with a value of reactance of negative J 1.079 ohm. Okay, negative. Okay, because this only capacitor can minus this inductor. So meaning that the total impedance here is only resistor. Okay, so thank you for the answer. So, okay. Actually, you don't need to calculate. Actually, from here, you can just give the value of the Z load by looking at the values of the inductor here. Okay, so I hope you clear on that. Okay, I have no other example. Okay, I think next week will be our last class. Okay, even though I think we have another week, I think, but I think for this course, I think next week will be our last class lah. Only the topic that we will be covered next week is only the superposition technique for the AC circuit, which is same with the DC circuit, but with additional of the AC elements. Okay. So for the superposition technique, I think I will give the lecture synchronous. Okay, meaning that you don't need to watch the pre-recorded video because it is a very easy concept because you have already learned in the DC circuit theorem. So we just need to do, I will refresh back on the theory itself first, and then we do some maybe exercise and so on. Okay. So, okay, any questions? Your test will be on 19th of January. And the question is straightforward, quite simple and straightforward. But you need to, I have highlighted something inside these lectures, okay, which is related to your second test. So I hope you got what I mean. Okay, so I think if there is no question, then we can dismiss our class. Okay, thank you very much. So, Assalamualaikum and have a very good day.
Waalaikumsalam, Doctor.
Thank you, Doctor.
Okay.
Thank you, Doctor.
Thank you, Doctor.
Thank you,
Thank you,
Doctor.
Doctor.
Doctor.